तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The last class we saw that the diode can be used in the breakdown region as a Zener diode, and it can be primarily giving you secondary power sources called Zener regulators, DC power sources. Now, today we will discuss how to design a Zener regulator. It is given that a DC voltage V I has been generated after it has been sort of stepped down or stepped up from the power supply using a transformer. Then using rectifier diodes, the unipolar conversion has been achieved for the voltage, and capacitive filter has been put, so that the voltage is essentially a unipolar DC voltage with very little ripple. That has been done, and that design we have learnt how to do. So, this is the output of such a converter, AC to DC converter, which obviously responds to input variations. If the input AC varies, the output DC will correspondingly vary, and therefore, we do not want this DC voltage to vary. We want a DC voltage which is going to remain constant, so that we can use this constant voltage in biasing all our active devices later, so that we can do the design properly. Now, such a regulator, when it is required, when the output DC is required to be regulated, that means it should be remaining constant at a given value with very little variation. One way of achieving such a thing is using this Zener regulator. So, this unregulated voltage V I is therefore called unregulated DC. What does it mean? It is permitted to vary from V I minimum to V I maximum. This is the variation resulting in sort of problem for us, because we do not know where exactly we can assume the DC to be remaining constant. It does not remain constant, it keeps varying. Suppose it varies, the operating point of all the devices will also vary correspondingly, and the design becomes difficult. So, how do we get this information about V I minimum and V I maximum? This can be got from how much your power supply varies. Let us say it is varying from 180 volts RMS to maybe 280 volts RMS. This kind of variation is possible, quite possible. Correspondingly, this will vary from a minimum to maximum. Corresponding to 180 volts, you find out what the DC voltage is. Corresponding to 280 volts, what the corresponding DC voltage is. You can then get the range of variation possible for V I. Then I am going to put a Zener diode. So, we know that the Zener breaks down at a specific value of voltage. Then it can maintain that voltage constant. Obviously, in order to limit the current in the Zener, I will put a current limiting resistance RS. This is essentially necessary, so that our Zener is going to have a current which at most can become equal to IS. So, Zener characteristic, you know already that it is going to be a diode characteristic which has a breakdown characteristic like this. The Zener diode can operate anywhere in this range of operation from the point where the voltage becomes almost constant and the current can vary to any value. This range is the region of operation for the Zener. Therefore, this point is very crucial where the diode has been reverse biased and the diode resistance is almost infinity here, and thereafter this current increases, the leakage current increases and it starts breaking down. The point where it becomes constant, the voltage becomes constant, this is called a knee point. This is the knee of the curve. So, this current is the knee current. This is specified by the manufacturer. So, one should know that Zener is operated as a Zener diode only above knee current. That means, the current through the Zener should be greater than the knee current, but obviously there is a limit on how much power this Zener diode can dissipate. So, that means this point here, another point, this is corresponding to P Z max, the power maximum. What is the power maximum? P Z max corresponds to V Z into I Z max. V Z is essentially remaining constant, and therefore, V Z into I Z max is the power that can be maximum power that can be dissipated in the Zener. So, this is also given by the manufacturer. That means, if power max is given, you will come up with the maximum current that can be permitted to flow through the Zener. So, that means, the Zener diode can be operated only within this current as a Zener diode. The current through the diode has to be always, that is I Z, should be always lying within this range, so that the voltage across the Zener is constant. That is the idea in this design. So, the idea in the design is that I Z can be permitted to vary only between I knee and I Z max. Now, you might wonder why it should vary. We know that V I varies from V I minimum to V I max. That means, the current in this I S, which is nothing but V I, here this voltage, minus V Z by R S. So, this is V I, this voltage, this is V Z. Therefore, the voltage across R S is V I minus V Z divided by R S. This current now can be therefore varying because V I is changing from V I minimum to V I maximum. That means, I S is going to change from I S minimum to I S maximum. How is that found out? Because this is changing from V I minimum minus V Z by R S to V I maximum minus V Z. This is the range of variation of this current. If this is changing from a minimum to maximum, obviously, the current in this is going to change from a minimum to maximum. Why? This voltage is essentially constant. That means, I L is essentially constant if R L is constant. So, if R L is constant, then I L is going to be constant. You are going to therefore deduct this I L from this. So, I Z is equal to I S minus I L. Due to Kirchhoff's law, I Z is going to be summation of this current plus this current. So, what goes in the load is removed from I S, that will be the current permitted to flow through Zener. So, in order that this voltage remains constant, I should see to it that I S minus I L, which is I Z, is maintained within this range at all times. If this is fulfilled, then the design is a good Zener regulator, because then I can assume that V Z is remaining constant. So, let us therefore write down the equations necessary for doing the complete design. We know that Is is varying from minimum to maximum. Then what is the Iz minimum to maximum? Iz minimum corresponds to, now you might say, sir, I can also have RL changing, because RL, okay, we are only designing a voltage regulator. Okay, current can be changing depending upon RL. So, IL can change, then we have to be careful. Iz minimum is nothing but Is minimum, okay, minus maximum of IL. So, that is the worst case minimum for the Zener. Suppose I take the maximum from the minimum value, that is the lowest current that can ever flow through the Zener. So, I can therefore find out, if I know the load variation, what the IL maximum is, then I subtract IL maximum from Is minimum, that is Iz minimum. What is Iz max? Going to be, now we will take Is max, subtract from this the minimum possible current, load current. So, we already have Is minimum and Is maximum from this in terms of Vi minimum and Vi maximum, and if you are told what IL max and IL minimum are going to be, then I would know what Iz minimum and Iz maximum. That means, I have to select what? RL is not under your control, Vz is the specified voltage to be regulated. Okay? So, it is regulated DC voltage, it is fixed. RL minimum and RL maximum are known to you, Vi minimum and Vi maximum are known to you. So, the only design parameter here, okay, to be considered is fix up Rs, fix up the value of Rs, so that Iz minimum and Iz maximum lie within this range, Ini and Iz max permissible for the Zener. That is really the design problem. So, just after this we will work out an example wherein we will in fact design this regulator for a specific variation in Vi and a specific variation in load. Consider example 15 now. Design a Zener regulator to give a regulated voltage of 6 volts. The moment that is fixed, we can fix the Zener now, the first part of the Zener. Zener voltage should be Vz equal to 6 volts. That is all. One part of the design is over. Voltage of 6 volts for a load current varying from 1 milliampere to 20 milliamperes. This current is varying because this load is changing, say 1 milliampere to 20 milliamperes. That can be also given in terms of load changing from 6K to about 30 ohms, right, 6K to about 300 ohms. Now, the input is supposed to vary from 10 volts to 15 volts. Fix up the value of Rs. Now, let us say we have taken a Zener, and from the Zener diode manual I can find out for 6 volt Zener what the knee current is and what is the maximum current. Let us say Zener chosen, this is has I z knee equal to let us say 0.1 milliamperes and I z max, which can be got from power maximum, okay, is equal to let us say 50 milliamperes. One thing you should select. How do I select this? Obviously, I z knee should be pretty low. Okay. I z max should be at least greater than the maximum current that is going to be given to the load. So, here 20 milliamperes. So, it should be greater than 20 milliamperes. So, that there is some current still left for the Zener. So, let us say it is 50 milliamperes given for this Zener, which is having a Vz of 6 volts. So, how do we do the design? Let us consider when the input is 10 volts, what should happen? Let us say input is 10 volts, the Zener is breaking down at 6 volts. So, 10 minus 6 is the drop across this. So, this is the drop, that is 4 volts, that divided by this has been taken as minimum. Okay. So, the minimum current now available in RS is 10 minus 6 divided by RS. Suppose RS is a range. I have not yet chosen RS. So, I would like to know what should be range of RS which is permissible for my design. So, 10 minus 6 is the minimum voltage available. For that I divide it by the maximum resistance possible here, that will give me the minimum possible current in this circuit. So, this is the minimum current, okay, Is minimum. That should be, okay, such that if I deduct from this 10 minus 6 by Rs max, this is the minimum current. I will take out the maximum current to be given to the load. So, that is 20 milliamperes. Now, this is what is left as the minimum possible current through the Zener, and that should be greater than, this current should be still greater than, okay, 0.1 milliamperes. Is this clear? So, we have taken the minimum possible current in RS, subtracted from that the maximum load current, arrived at the minimum possible current that can be permitted through the Zener, at which time the Zener should still function satisfactorily. That means that current should be greater than the knee current, which is 0.1 milliampere. Now, this equation should give us the value of Rs max. Next, when this is 15 volts and I deduct from this the Zener voltage 6, 15 minus 6 is the maximum voltage drop here. So, that is going to lead us to the maximum current Is, if Rs is minimum, right. Under that situation, that is the possible maximum current, and I deduct from this the minimum current. This is actually Is max. From this Is max I deduct the minimum current, that will be then left with the maximum possible current through the Zener. So, this is going to be 9 by Rs minimum minus, how much is it? 1 milliampere that is the minimum load current, and that should be, this is the maximum current. Okay. This should be less than the maximum possible current for the Zener, which is given as Iz max, which is 50 milliampere. So, this equation, which is nothing but 4 by Rs max minus 20 into 10 to the power minus 3 should be greater than 0.1 into 10 to the power minus 3, which is actually speaking 20.1. I am going to shift this over to this. So, 20.1 so Rs max, can take it there, 4 divided by 20.1 milliamperes. Okay. Rs max, okay, will come here. This will be 4 into 4 divided by 20.1 K. 4 divided by 20.1 K should be greater than Rs max, or Rs max should be less than, okay, 4 by 20.1 K. Okay. Is this clear? Now, that is that equation. Here 9 by Rs main should be less than, this is 50 milliampere, this is 1 milliampere. So, 51 milliamperes. So, again Rs minimum is 9 by 51 milliamperes, or 9 by 51 K, 9 by 51 milliamperes, or 9 by 51 K, or Rs minimum should be greater than, right, 9 by 51 K. So, now we have calculated these resistances. Rs max is 4 by 20.1 K, which is 199 ohms. Rs minimum is 9 by 51 K, which is 176 ohms. That means the Rs that you have to select, Rs has to be such that 176 is less than Rs and 199 is greater than Rs. Okay. And in fact, 176 is less than Rs and Rs is less than 199. Okay. This is the range. So, the preferred value in this, we will select Rs as 180 ohms. These resistances are available. You select any preferred value within this range, 180 ohms. Now, for this resistance, we have to give specification in terms of its wattage. So, the power dissipation in the resistance maximum is Vs max, that is Vs squared divided by Rs, which is the maximum drop across this is when this is 15 volts minus 6, that is 9 squared divided by 180 ohms, which is 81 by 180 ohms, which is equal to 450 milliwatts. So, that means I can select the resistance as 180 ohms half watt. These are standard resistances available for you to design the whole thing. Now, the design is complete in the sense that we know the resistance Rs to be chosen and we know the Zener to be used along with this, and the Zener regulator, if it is connected this way, it will work satisfactorily, that we know. Now, some finer points regarding the design I would like to mention. That this Zener regulator, I would like to see how it functions in terms of the graph. This is the theory, right? Graph. Let us see here. This, please remember, is similar to what we did in the case of a diode and load line concept. Even here, we can bring about the load line concept. This is the diode characteristic. So, Zener diode characteristic is this, and we know that V I minus V divided by R S is another equation to be satisfied. Okay. So, this is going to be the current, okay, I S. If the other load resistance is infinity, if let us say R L is, okay, open circuit, that is R L value is infinity, then I can say that I S is same as I Z. So, I S becomes same as I Z. That situation, it is simple Zener diode circuit, V I, R S and a Zener. Okay. It is not complicated, and the Zener current is same as I S. So, under that situation, we can say that this equation is this. Okay. This is the voltage V, which is now equal to V Z. Okay. So, V I minus V Z by R S is the current I S. So, this is the equation that is plotted here, equation of a straight line with slope equal to 1 over R S, minus 1 over R S here. Both current and voltages are negative. So, 1 over R S, and this is the operating point for the Zener, or this is the Q point. This we had referred to the diode circuit also earlier, okay, diode Q point. Here the Zener Q point, the Zener is quiescent at this point. So, you can see here the Zener voltage is almost constant there. So, it is V Z, and therefore, it is very simple to obtain the operating point. If V is very close to V Z, then I S is nothing but I Z is equal to V I minus V Z by R S. That is what this gives as the current. This is the current of operation. So, suppose V I varies from, let us say, 10 volts to 15 volts or whatever it is. For another voltage of V I, the slope remains the same. So, this is a parallel line. So, it is shifting. So, the operating point shifts here. So, what did we do in the case of diode circuit? We said this variation may be so small that this is assumed to be linear. That means, this is essentially going to remain very nearly constant at V Z. Okay. Only this current is going to change now to a new value, which is the new value of V I minus V Z by R S. Now, if this is vertical like this, there is absolutely no change in voltage, okay, only the current changes. If it is not vertical, if there is a small slope, that is the case with Zener diodes, okay, this slope, which is nothing but delta V Z divided by delta I Z around the operating point I Z, that is the slope. Delta V Z, inverse of the slope is delta V Z by delta I Z, actual slope is delta I Z by delta V Z. So, if this is vertical, this resistance, this is called the Zener small signal resistance, small signal equivalent resistance. Typically, for this Zener diodes, it is of the order of tens of ohms. So, tens of ohms. In fact, this resistance, which is of the order of tens of ohms, may be really negligible compared to the series resistance that you are putting here. Okay. That means essentially this slope is almost vertical compared to this slope. That is what it is. That means most of the change in the current is brought about by the change in voltage here, okay, and that will directly tell you, okay, that the change in current and the change in voltage, okay, they are related linearly if you were to replace this by means of a linear resistance. Now, what is the change? If you are interested in change, I told you, you can replace the whole circuit only for changes in terms of the equivalent circuit. What is it? So, let us say that this is the change delta V I that is occurring. Change in voltage is from 10 volts to 15 volts. Okay. So, delta V I is 5 volts. So, for the change in voltage, this resistance is remaining as whatever R s, okay, and the Zener diode, if it is an ideal Zener, right, you would have represented it as a battery with Vz, simply battery. So, no change occurs here at all in the voltage of the Zener, right, across the terminal of the Zener, irrespective of the current in this. So, you can always assume this to be constant. So, you can replace it by means of a battery, okay, and then of course, you can put down the load. This is the case if this were absolutely vertical. So, there is no change in Vz. So, I can replace it by means of a battery. If it is not vertical, then I will say that there is a series resistance associated with it. So, I will replace it by means of an equivalent circuit, which is R small z and a battery. So, as far as this battery is concerned, it is of no consequence for changes. So, it is a short circuit. Okay. So, the equivalent circuit of a Zener diode for the whole thing is a battery in series with Rz. For the changes, please remember, once again let us put, if it is this Vi, then I have to put this for the whole voltage as a battery with Vz, and then this will be the V naught, total V naught. This is the complete equivalent circuit for the Zener. Now, for the changes, I can simply, since I can apply superposition now, it is a linear circuit. For this voltage, I can separately find out all the situations, and for this voltage, I can again find out the situations. So, I would like to see it for only the changes, that means this battery with delta Vi change Rs, Rz and RL. So, this is the circuit which will give you all the changes in currents and voltages that will now occur. Let us use this. This is delta Vi. So, what is the change in current in the circuit? That can be easily obtained by delta Vi divided by Rs, this is one resistance, plus Rz parallel RL. This is essentially Rz is so small, okay, and RL may be also small. Essentially, Rz parallel RL is negligible compared to Rs. So, it might become essentially delta Vi by Rs. Okay. This is the current limiting resistance, okay, earlier that has been put. typically in our example we have chosen, it is 180 ohms we said, and this is tens of ohms and shunted by resistance of the order of 300 to 6K. So, essentially it is RZ itself, and therefore, it is essentially delta Vi by Rs in this problem. Now, what is the change in voltage at the output, I would like to know. That can be evaluated by multiplying this current by effective resistance here, which means this into RZ RL divided by RZ plus RL. Okay. So, we can say that this is delta Vi into RZ RL by RZ plus R, or essentially approximately equal to delta Vi by Rs into Rz, because Rz parallel RL is Rz itself. Okay. So, you can see that the change in voltage here, typically let us see in this problem that we have chosen, change in voltage is 5 volts. So, for a 5 volt change in voltage, this is, let us say Rz is 10 ohms. This must be given by the manufacturer. What is the typical value of Zener resistance? Manufacturer will tell you for this kind of Zener around the operating point what the Zener resistance is, 10 ohms let us say, divided by Rs in this case is 180 ohms. So, you can see that the voltage is simply 5 by 18 volts. So, it is much reduced. That means, change in voltage is very much reduced at this point. This you can note, because this Zener diode is basically equivalent to a battery. If it is a battery, the change in voltage would have been 0. It is not a battery. It has a series resistance of Rs. Because of that, when there is a change in voltage, there is going to be a small change in voltage here, okay, in the Zener. That is the delta Vz, and that we could calculate by using the equivalent circuit for the diode. So, if somebody says that the voltage changes by this amount here, we can always find out what the change in voltage is, which is extremely small, okay, around the Zener voltage by using the Zener equivalent. Further, we can also do what is called as ripple reduction here. Let us say this is a different thing. At a given voltage, let us say at 10 volts or 15 volts, the voltage DC voltage is not going to be just DC voltage. The DC voltage itself is changing from 10 volts to 15 volts. But along with this DC voltage, we have what is called ripple. That if we use a half wave rectifier, that ripple frequency is 50 hertz. If we use a full wave rectifier, the ripple frequency is 100 hertz. So, we know how to evaluate the peak to peak ripple in our earlier method of evaluation of ripple etc. We have understood that. So, apart from a DC voltage, there is a ripple here, peak to peak. So, it is not just a DC voltage of 10 volts, there is going to be a ripple here, something that is varying. So, that ripple also gets reduced here by this factor, which is Rz divided by Rs, because of putting. So, there is a ripple reduction, and therefore, if there is some ripple factor here, the ripple factor here is much reduced. That is an advantage of using the Zener regulator. So, ripple reduction factor is also by the same amount. Please understand that this is different from what I discussed previously. When the voltage itself changes from a minimum to maximum, the operating point of the Zener will change from minimum to maximum, and the Zener current will change from minimum to maximum, and then there is a little bit of variation in the Zener voltage. So, we can no longer consider Zener is going to remain at 6 volts. No, it is going to vary to a certain way. That variation can be found out from the equivalent circuit. Okay. Apart from that, we can also find out when there is a ripple riding over the DC voltage, how much ripple reduction occurs here. So, the 6 volts, apart from being slightly different from 6 volts, how much is the ripple that is going to be riding over the 6 volts also can be found out by using the same equivalent circuit. This equivalent circuit is more valid for ripple reduction than for this large voltage change. When there is such a large voltage change from 10 volts to 15 volts, maybe it is not right to assume that this is linear. Okay. Whereas, definitely the ripple itself is a small change over 10 volts, and for that small change in 10 volts we can put down this equivalent circuit without any hesitation whatsoever. So, this kind of problem we can discuss whenever we are confronted with obtaining a absolutely invariant DC, okay, when AC is varying. Such Zener regulators are quite common as secondary power sources, wherein such regulation is very important, so that the operating point is known to the designer beforehand, and therefore, he need not be worried about the variation that is occurring in the power supply. Let us now consider an example which is a total design. Starting from the power supply 220 volts 50 hertz, I would like to know whether the Zener regulator that I have designed, okay, can be fed from such a source, and how to do the design of the transformer and the capacitor here. This is important. We will see the how to fix up the value of N and how to fix up the value of C. Now, we have known that this input voltage was assumed to be varying from 10 to 15 volts, and we will take nominally at 220 volts. Okay, the voltage is corresponding to 12 volts we will take, right. Correspondingly, we can fix 10 and 15 as the maximum and a minimum and maximum variation at the secondary of this point. Now, for such a thing we will design a transformer and fix up the value of capacitor. How to do that? Now, the voltage here, the DC voltage, peak voltage here should be 12 volts. Okay. So, 220 root 2 divided by N is the sort of peak voltage on the secondary side, and therefore, that is to be equated to 12 volts, and N is got as 25.9. This is simple. This follows the same procedure that we followed in our earlier solution of different problems connected with the converter, AC to DC converter. The variation comes only in this: how to select the value of the capacitor. At this juncture, the load is going to be given to you not in terms of the resistance. 180 ohms is given as the resistance. This is not to be taken totally as the load. Load is different, because we have connected the Zener here. If this is getting charged to 12 volts, this is 6 volts. The drop across this is now 4 volts, 12 minus 6, 4 volts, and the current in this is fixed. Okay. 12 minus 6 is 6 volts. Okay. So, 6 volts by 180 is the current in this. 6 volts divided by 180 is the current in this. So many amperes, or this into, okay, 6000 by 180 milliamperes. So, that is 6000 by 180. That is 33.3 milliamperes. So, that should be taken as the current constantly being drawn from the capacitor. That is, capacitor is getting discharged by a current like this. That means, let us see, if this is the current I, which is constant I DC, that divided by C, okay, is the rate at which capacitor voltage is getting reduced. That into T is the peak to peak ripple for the circuit here now. Please remember, this current has been evaluated by finding out the drop across 180, which is 12 minus the Zener drop, that divided by 180 is the current. Okay. So, this is the difference in design of a circuit with Zener regulator as compared to circuit without any regulator. Right. In the case of circuit without regulator, the current is going to be voltage divided by the resistance. Right. Here this voltage minus this Zener divided by the resistance is what is going to be, and this load variation is of no consequence. The actual load variation is of no consequence as far as this design is concerned. From the capacitor, the discharge current is always going to maintain constant irrespective of the load resistance. So, this is the point that you have to bear in mind while designing such combination of circuits. Okay. Let us complete this. This I is 33.3 milliamperes divided by C into T, which is 20 milliseconds. So, from this, if you are specifying the peak to peak ripple, you can find out the capacitor, or if the capacitor is known, you can find out the peak to peak ripple. So, let us say we are fixing up the capacitor at 500 microfarad. Okay. Then the peak to peak ripple is going to be, if we select this as this thing, then 33.3 into 20 to 10 to the power minus 6 divided by 500 to 10 to the power minus 6. So, that is the peak to peak ripple, which is going to be roughly, how much is it? So, okay, 100 to 100. So, this is going to be the 1.3, 1.33. So many volts is the peak to peak ripple. Okay. Now, we have found out the peak to peak ripple at across the capacitor. So, you want the peak to peak ripple at the load. Now is the time you can now the peak to peak ripple at across the capacitor is 1.33 volts. This into Rz divided by Rs, as we did in the last example, okay, which is 1.33 into 10 ohms divided by 180 is the peak to peak ripple. This is across C. This will be across the load. Okay. So, you can see that there is a reduction by a factor of 18 across the load for the peak to peak ripple. So, the design now is complete. Okay. You have made use of the small signal equivalent circuit for the Zener in order to evaluate the actual peak to peak ripple that is occurring across the load resistance. So, whether it is design or analysis, you must adopt all these procedures in the case of AC to DC converter, where the DC voltage is supposed to be regulated.